Good morning, Professor Santan. So you can start.
Yeah, okay, I will begin.
Okay, thank you very much.
Thank you. So is everyone able to see the slide?
Yes, sir.
Okay. So we had gone through some theory the last time. Today we will look at some calculations. Okay, and some of you might have gone through this before, but we will go through these 2D fracture models, and we will calculate. I mean, we will calculate the parameters for one of the fracturing jobs. Okay. So generally, so some of the methods for calculating the hydraulic fracturing parameters. So first of all, it is a matter of debate whether whether a single fracture or multiple fractures are created in a hydraulic fracturing job from one set of perforations. So both cases have been evidenced based on the information collected from tilt meters and microseismic data. Okay, but for our case, for these calculations, we will assume that each of those perforation cluster, there is one fracture propagating from the wellbore uh, during the hydraulic fracturing, okay, when we start pumping the fluid. So if we talk about a single fracture propagating from the wellbore, it's a sheet-like fracture. So there are three models for modeling that. Okay, so the first one is a penny-shaped crack, which is called the radial model. The second one is the KGD model, Kristianovic, Gretzma, and de Klerk. And the third one is the PKN model. Okay. So this penny-shaped model was first proposed by Snedon in 1946. Then in 1969, Gretzma, de Klerk provided equations for maximum and average apertures of penny-shaped crack. Okay. Just a second. Can you? What do you see on my screen? Do you see PDF or what do you see? Hello, can you hear me or no?
Sir.
Wait. Uh, okay. So what happened is so here you have the Kristianovic, so three of these models, okay, and then so first one, let us discuss the penny-shaped crack. Okay, so in this case, you have what? You have the wellbore. If we are talking about a horizontal fracture, then we have this wellbore. And if you're talking about a vertical fracture, then this is the wellbore. The wellbore is horizontal in this case. And in case of a horizontal fracture, the wellbore is, I'm just showing it to you like that. But this is a simple radial model, okay? And So this is the 1946 model by Snedon. When there are no barriers containing the height of the fracture, then it will just grow out of the wellbore like a radial, like a circular fracture, okay? Because, for example, if you have a massive sandstone, then what will happen? The fracture will grow radially from the wellbore. And if it's a horizontal fracture, then obviously there is no vertical growth barrier, okay? It will just grow in a circular direction from the wellbore, okay? But this is rare. So this type of fracture is rare. You never find a fracture which is completely circular, okay? Then aperture of a penny-shaped crack. So if you talk about this penny-shaped crack, so these guys already calculated the aperture, which is width at the wellbore. So this is it, okay? So width of the fracture, this means the opening of the fracture at the wellbore. So this is the width, okay? So this is the width here, W. And this is the pore pressure inside the fracture, and this is the radius of the fracture, okay? So if you want to calculate the width, so width at the wellbore, right there, okay? So this is the formula. So it depends, the width depends on what? It depends on the fluid viscosity that you are pumping, the flow rate, which is the pumping rate. Then we have R, which is the radius of the fracture, Poisson's ratio, and Young's modulus. But what happens in this fracture is, as you go away from the wellbore, the width of the fracture will reduce, as you can see in this picture. You see, as you move away from the wellbore, the width of the fracture is reducing. Right at the wellbore, the fracture width is the highest, okay? And obviously, this is the width at the wellbore. And if you take an average width, it's going to be smaller than that, right? Because average width is less than the width at the wellbore. So average width, if you calculate, instead of 2.56, you put 0.85 here. So that will give you the average width. All the other parameters stay the same. Now let's talk about the KGD model, okay? Which is this one. This one. So in this case, the average width is given by 2.56. So we sorry, this is the width at the wellbore, WW, okay? So 2.56 times mu, which is what? Fluid viscosity, Q is the flow rate, 1 minus Poisson's ratio, radius, Young's modulus, to the power 1/4. And if you talk about the average width, all of these will be there, except you will have a W of, so this is the penny-shaped crack, okay? Then if you talk about the KGD model, which is this one, okay? So in this case, what are you seeing? The fracture is going out of the wellbore, and it has a fixed height with height HF, which is the fixed height, okay? And then half length of the fracture, which is called XF, okay? This is the half length of the fracture. We are talking about the KGD model now, okay? Which is this one, KGD, okay? So that is the fracture half length, and you can see the width of the fracture. What is happening to the width? See, there is a fracture tip here, okay? At the tip, the width has gone to almost 0, okay? In this case, you have to assume for KGD model that the height of the fracture is much greater than its length. So what is height? This is the height of the fracture from there to there, okay? I hope you can see my cursor. Okay. So height will be much greater than the fracture length, which is from there to there. That is the assumption for this KGD model, okay? And we assume that the flow rate in the fracture could be approximated by a constant pressure in the majority of the fracture body, except for a small region near the tip with no fluid penetration and hence no fluid pressure. So it means that it's assuming that the pore pressure is not changing within the fracture except at the fracture tip, okay, small region. So the width of this fracture, the average width, W bar, okay, is 0.29 times flow rate. Mu is what? Fluid viscosity, 1 minus Poisson's ratio, fracture half length, which is your XF, like this, okay? Square divided by G, okay? G is what? It is the shear modulus of the rock. Shear modulus formula is Young's modulus here divided by 2 times 1 plus nu. Okay. And then HF. HF is what? The height of the fracture times pi over 4. Okay. So this is the average width of a KGD fracture. Then if you talk about the PKN model, which is this one. So this is the PKN model. In this case, you have to assume that the length of the fracture is much greater than the fracture height. So this is the PKN model in 1961. So the Perkins, Kern, and Nordgren, they came out with this model. And then in 1972, Nordgren added the leak off and storage within the fracture due to the increase in the width. And this formula, so this is named as PKN. So Perkins, Kern, and Nordgren. Okay. So the average width of a fracture here is Q mu 1 minus nu XF. XF is what? XF is the fracture half length here, as you can see here, XF. Okay. Divided by G is the shear modulus, and then pi over 4 times gamma, where gamma is 0.75. Okay. So this is the average width. And you can see in this case, the width of the fracture changes from place to place. Okay. So here it is less, here it is more near the wellbore. Okay. So slight difference between the formulas of the PKN and KGD. Okay. So this is your KGD and this is PKN. Okay. So in both of these formulas, you have to assume a given fracture height and you have to assume a fracture length, okay, before you can start your calculations. Okay, so let's take a look at the calculation, and let us first take a look at the steps you use for the calculations for a fracture job. For example, if you want to design a fracture job, you have to calculate a lot of parameters. So how will you calculate those parameters? For that, there's a lengthy calculation. Let us take a look at this calculation, okay? So one thing to remember is greater the probed fracture length and greater the proppant volume, the greater the production rate of the fractured well, okay? So higher the length and more the proppant you pump, higher is the production. Okay? So that has been observed from different experiences. So let's take a look. So first you have to assume a fracture half length XF and the injection rate QI. Injection rate depends on what? It depends on the amount of, it depends on the power of the pump that you are using, okay? So if you have many powerful pumps, you can increase your injection rate. If you cannot pump at a very high speed, then your injection rate will be lower, but it is the pump which determines your injection rate, okay? Then if you use the material balance formula, then what do you get? Total injected volume is equal to what? The amount of volume in the fracture plus the amount of volume that leaked off from the fracture. Okay, so this I hope makes sense. It's just a material balance. Okay, V injection equal to V frac plus V leak off. So something that leaks off into the matrix is a V leak off, and the fluid amount that stays in the fracture is V fracture, okay, while you are pumping. So V injection, so total volume injected is what? Pumping rate, this one, times the total amount of time you pumped. So volume equal to meter cube per second times second, so it will become meter cube, yes? So that is V injection. V frac is what? It is the volume of the fracture is what? Area of the fracture times the width of the fracture. So what is that? It is the area, so this much, okay? Area of the fracture times the width of the fracture, okay? So that is the fracture volume. And how much is the leak off? What is this parameter? It is 2 times K sub L, C sub L, AF, RP root over T. So what are these terms? So so CL is what? It is the leak off coefficient, and you can determine that from different types of laboratory measurements. Okay. Then you have the area of the fracture, which I just showed you. So area of the fracture is what? It is the 2 times the half length, okay, times the height of the fracture. Okay, that would be the area of the fracture. Okay. RP is what? It is the ratio of the reservoir thickness to fracture height. Ratio of reservoir thickness to fracture height. So let's go back to this picture. So in this case, if you talk about, so let's say this is the reservoir, okay, and this is the fracture. So fracture height would go from there to there, okay, while the reservoir is there up to there. So you can think of the ratio of reservoir thickness to fracture height. If your reservoir is if your reservoir has higher thickness compared to the fracture height, then that ratio will be greater than 1. Okay. So that is your RP, and root over what is TI? T is the total amount of time you injected the fluid. Okay, and KL, K sub L, it depends on these parameters, eta and pi. Okay, what is eta? Eta is not viscosity. Okay, eta is actually the fracture fluid efficiency. This means out of the total amount of fluid that you pumped, how much stays in the fracture? That is the fracture fluid efficiency. Okay, so that is the fraction of the fluid that stays in the fracture divided by the total fluid pumped. So this KL depends on the fluid efficiency. So once you get this, all of these numbers, you can calculate the leak off volume. Okay. So as I already told you, RP is H divided by HF. Then area of the fracture is 2 times the fracture half length times the height of the fracture. Eta is what? It is the eta is the fluid efficiency. So V fracture divided by total volume injected. Okay, V pad. Pad is what? Pad volume is what? Pad is the amount of fluid you pump. V pad is the amount of fluid you pumped without any propellant. So it is, you just pumped the slick water into the fracture. Okay, so that is your V pad. Okay. Okay, then look at this formula. CP T equal to CF 1 minus T pad divided by T injection minus T pad to the power epsilon. So CP is what? CP is the propellant concentration in the fracturing fluid at any given time. Okay, so please remember, propellant concentration in the fracturing fluid at any given point of time. CF is the final propellant concentration in the fracturing fluid. Okay, so highest amount of propellant concentration in the fracturing fluid is CF. T is any given time minus T pad. T pad is when you stopped pumping the slick water and start pumping the propellant plus slick water. Okay, so this is the slurry stage. So okay, this is when you start pumping the slurry. Okay, and T pad means what? It is the amount of time you just pump the pad water. Okay, I mean clean water. And T injection is the total volume of so T injection is the total amount of injection time minus T pad. Okay? And epsilon is what? Epsilon equal to 1 minus eta divided by 1 plus eta. So this means epsilon is what? It is the fraction of injected fluid you want to pump as pad. Okay, pad means clean water. So the fraction of total injected volume you pumped as pad. Okay, that is epsilon. So after you have calculated all that, now you can predict the fracture width using this formula. So the width of the fracture is equal to C sub P divided by 1 minus porosity of the propellant pack times the density of the sand in the propellant. Okay, so this is the final width of the fracture or average width of the fracture. So let's begin from bottom here. Okay. So what is C dash P? C dash P is the average concentration of propellant in the pumped fluid. Okay, and this is the final concentration of propellant in the pumped fluid, as you remember from this formula. Okay, so this is the average concentration of propellant in the pumped fluid divided by maximum concentration of propellant in the pumped fluid divided by 1 plus epsilon. And what is epsilon? Epsilon is this. Okay, then from this you get the average concentration of propellant in the pumped fluid. So if you multiply the average concentration of the propellant in the pumped fluid times total volume injected minus the pad volume, you get the total mass of the propellant that has been pumped during the fracturing job. Okay, so this is M sub P. So you can see the mass is what? What is the unit of mass? It could be kg or pounds. Okay, what would be the unit for this one? C sub P. It would be what? Pounds of propellant per gallon of volume or per gallon of fluid. Okay, so that would be pounds per gallon. What is this CP? CP, C sub P, capital C sub P is what? The mass of the total propellant pumped divided by the total area of the fracture. Okay, so this is the amount of fracture per unit foot, sorry, amount of propellant per unit foot of the fracture. So suppose this is the fracture. Okay, so amount of propellant per unit foot square, I mean per foot square. Okay, so this means if this is 1 foot square of the fracture, how much propellant will be there? So this would be pounds per feet square. Okay, that would be the unit of this. So now you know all the formulas, and now let us take a look at the calculations. So I took this from Boyun Guo. There is a author, Boyun Guo. So I took it from this book. Okay, so let's say the pay zone thickness is 70 feet that you want to fracture. Young's modulus of the rock is 3 into 10 to the 6 psi. Poisson's ratio is 0.25. Fluid viscosity that you are pumping is 1.5 centipoise. Leak off coefficient that you determine from the lab probably is 0.002 foot per minute to the half. Propellant density is 165 pounds per feet cube. Propellant porosity is 40%, so that is 0.4. And the fracture half length is what? Is 1000 foot. Okay. So and then the fracture height that you get is 100 foot. Then the fluid injection rate is 40 barrels per minute. So this is determined by how much, what is the pump strength that you have. And the final propellant concentration in the fluid that you would like to plan for is 3 ppg, pounds per gallon. Okay. So given all that, and assume a kgd fracture, estimate the total fluid volume requirement. Okay, this one. Propellant mixing schedule. So how will you keep increasing the propellant concentration from time to time? That is the propellant mixing schedule. Okay. Propellant weight requirement and the propped fracture width. So this is important because this is what determines the fracture permeability. So this is what will produce your oil and gas later. Okay. So all of these things we need to design. So we are assuming a KGD fracture. So the first step is to what? Calculate the average fracture width using this formula. Okay. So let's say this is the KGD model. So we will use this formula here to calculate the average fracture width. Okay. So average fracture width is 0.29 times Q is what? The flow rate. That is the pump rate, which is 40 barrels per minute. Mu is viscosity, so 1.5 centipoise, as you can see here, 1.5 centipoise. 1 minus Poisson's ratio. Poisson's ratio is how much? 0.25. Okay, so we are given that 0.25. Okay, so 1 minus 0.25. Fracture half length XF is what? 1000 feet. So 1000 square divided by, you have the shear modulus. How will you calculate shear modulus if you are given the Young's modulus? So Young's modulus, how much are you given? 3 times 10 to the 6 psi. Okay, So now you have to calculate Young's modulus. What is the formula I told you? So if you want to calculate shear modulus from Young's modulus, you will use this formula, E divided by 2 times 1 plus nu. Okay. So that's what we are doing here in this calculation. So E divided by 2 times 1 plus nu. Okay. So you see this formula there, times 100, which is the times 100 is the fracture height. Okay. So once you do this times pi by 4, so you will get 0.195 inches. So almost 0.2 inches of fracture width you should get on average, okay, based on the KGD model. So what is the area of the fracture? 2 times fracture half length times the fracture height. So 2 times 1000 times 100, which is 2 times 10 to the power of 5 foot square. Okay. Then we use this formula. We use the volume balance formula, which is total pumping rate. I mean the total volume pumped, which is the total pump rate times the total time you pumped, equal to average, which is the area of the fracture, times the average fracture width, plus this term that you have seen before. So look at this. Which terms do we know and which we do not know? Q we know, which is 40 barrels per minute. And if you want to convert barrels per minute to what? So what is 5.615? So barrels to feet cube, if you want to convert. So because we are trying to convert everything into feet cube, okay? So so this is barrels, and this is, if you multiply with 5.615, it becomes feet cube. Then Ti, which is the total injection time, which we don't know yet, equal to area of the fracture times the fracture width. We already calculated the fracture width here, okay? But now we want to calculate in feet. So 0.195 divided by 12 plus 2 times, okay, KL is something we do not know. So for this, you assume KL equal to 1.5. So put this 1.5 here. And then area of the fracture is what? 2 times 10 to the minus 3. So 2 times 10 to the minus 3. Let's see. Oh, sorry, it's 2 times 10 to the minus 10 to the 5 feet square. So this is the area of the fracture, okay? Then 70, so which is your RP? RP is what? 70 divided by 100, which is the ratio of the reservoir to fracture height, root over Ti, which is the total injection time, okay? And this number, 2 times 10 to the minus 3, is the leak off coefficient, okay? So you can see from the leak off coefficient here is 2 times 10 to the minus 3, okay? That number we are putting there. So if you put all of that, then you can solve for root over Ti or Ti, okay? Ti is the what? Total injection time. And Ti you have here as well as there. So you need a solver, and you solve it and you get 37 minutes. So you need to pump, your frac job will be a total of 37 minutes, okay? So you will keep pumping for 37 minutes. So the problem now is that we have assumed a KL value. We need to check whether our KL value is correct or not. So the next step we do, we know the V injection. The total volume injected is what? Flow rate times the total time. So flow rate is what? 40 barrels per minute times 37 minutes we found there. So 37 here, 37, okay? And if you want to convert this volume into gallons, then you multiply with 42 here. So now you get a total volume of 6.26 into 10 to the power 4 gallons. Okay? This is what you need to pump. So if you pump so much, what is the volume of the fracture? So volume of the fracture is what? Area of the fracture times the average width of the fracture. Area of the fracture is what? 2 times 10 to the 5. So that is your 2 times 10 to the 5 here. Okay. Width of the fracture in foot or feet is how much? 0.195 divided by 12. And if you want to calculate feet cube to gallon, then you multiply with this, okay? you multiply with this number. So at the end, you will get the V frac equal to 2.43 in 10 to the power 4 gallon. Okay, so this is the gallon volume of the fracture itself, not the total volume. Okay. Then I told you what is eta. Eta is what? It is the amount of fluid in the fracture divided by the total fluid injected. Okay. So V frac, you know, is 2.43 into 10 to the 4. You put it there. V injection, you know how much? It is 6.26 10 to the power 4. So you divide this by that and you get 0.3875. Okay. So what is 0.3875? It is the amount of fluid that stays in the fracture divided by the, so all, this means what? 38% of the fluid that you pump stays in the fracture and rest goes into leak off. Okay, that's what it means. So now calculate KL again. K sub L equal to half times 3 over 8 eta plus pi 1 minus eta. I've told you this formula before. I've shown you this one. Okay, where did I show you this formula? Look at this formula. Okay, it is the same formula that we are using now. So KL equal to this. So once you calculate KL from here, you get KL is equal to 1.48. So now the question is this 1.48 very close to 1.5 that you calculated from here or no? Yes or no? So yes, 1.48 is very close to 1.5. This means all your calculations are correct. Okay. Suppose this number was way off from that number here, KL equal to 1.5. Then what will you do? You will insert this number here and recalculate all your other stuff. Okay. Until you keep getting similar values, and only then you can confirm that your calculation is correct. Okay. So I've shown you a flow chart here. So first, using this formula, calculate your T sub I, total injection time. From that, calculate your total injection volume. Once you calculate your total injection volume, calculate your V frac, the amount of fluid in the fracture, which is this one. Then calculate eta here, V frac divided by V injection. From eta, calculate your KL. And now if this KL is similar to the assumed KL, then you are okay. Otherwise, keep repeating this in loop until you get the KL values very close to each other. Once those are very close to each other, then all your calculations are correct, like eta or V injection or injection time, all of those are correct. Okay. Next step is calculating the pad volume. This means how much fluid are you going to pump into the fracture before you start pumping the slurry. Okay. So epsilon is the pad. So epsilon is the what amount? Oh wait, one second. Okay, so epsilon equal to 1 minus eta divided by 1 plus eta. So this is equal to 0.44. You get 0.44. So V pad equal to V injection times eta. Okay, V injection we already calculated in the previous step. Eta we know now. So this is 0.44. So if you multiply this, you get 2.76 times 10 to the 4 gallon. Okay, this means what? This is the amount of fluid you will pump as pad, and the rest of the fluid you will pump as slurry. Okay. So if you divide this total volume with the pump rate, which is your 40 BPM, what will you get? So this is what? If you call it meter cube, and if your pump rate is in meter cube per second, then you should get what? You should get second unit, right? So this is the total amount of time you need to pump. So if you do this calculation, you will get 17 minutes. This means for 17 minutes, you have to pump only the fracturing fluid and no slurry. Okay. Now that you are done with this, the remaining 20 minutes, so you calculated how much? Total time is 37 minutes. Okay. Out of which 17 minutes, you will pump only what? The pad volume. So now you are remaining 20 minutes. So now for those 20 minutes, you have to keep increasing the propant concentration. So how will you design that? So this is the propant mixing schedule. You have seen this formula before, C times P. So sorry, C sub P equal to C times P equal to final propant concentration in your fluid times T minus 17 divided by total injection time minus total pad time. Okay, so this is the pad time and this is the total injection time and this is any arbitrary time t. Okay, and I told you this value 3. Where are we getting the 3 from? We are getting from here. Final propant concentration is 3 ppg. You can see here. So you put 3 there, and now what will you do? You plug in different values of t. So look at this table. Okay, in the first value we plug for t is 0. So obviously, as long as this number is negative, then it does not mean anything. So until you get to 17 minutes, your Cp is 0. The propant concentration in the fluid is 0. Once you cross 17 minutes, only then you start increasing the propant, start putting the propant. Okay, so let's say at 20 minutes, if you put 20 there, okay, then you will get a number of 1.30. This means after 17 minutes, you should increase the propant concentration in your fluid to 1.3 ppg, pounds per gallon. Then if you put 23 here, then you will get, so for 23 you are getting what, 1.77. This means for the next 3 minutes you pump at 1.77 ppg. Then for the next 3 minutes you pump at 2.11 ppg, and like that at the end for the last 3 minutes you will pump how much? 3 ppg. Okay, and that is what we are mentioned, that the fluid propant concentration at the end, final propant concentration is 3 ppg. So you are getting 3 ppg. Okay, so this is how you will design your fracture, the treatment job. So you can see from this graph, okay, slurry concentration on the y-axis and injection time on the x-axis. So for the first 17 minutes, you did not put any propant, so the slurry concentration is 0. This means it's the pad time. After that, you gradually increase your propant concentration until you get to 3 ppg. Okay, you can see 3 here. So this graph was built. This graph was built using data from this table. Okay. So the next question we have: how much total volume of propant we need to pump? Okay. So for that we need to calculate what? Let me show you. So we begin from this formula. We begin from this. So what is Cp? It is the average concentration. This one, the average concentration of propant in the fluid. Okay. So if the maximum is 3, then 3 divided by 1 plus epsilon, which is 0.44, you will get some number. So that will be what? Average propant concentration in the fluid. Okay. Then the mass is what? Whatever value you get from there. Sorry, whatever value you get from C-P, you multiply that with V injection, total volume injected minus the pad volume injected. And once you get the mass, then you get the concentration of propant in the fracture, which is what? Pounds per feet square. Pounds of propant per feet square of fracture. So that would be your mass you get from there divided by the area of the fracture. Okay, so that's what we are doing here. So you know that CF was how much? 3. So 3 divided by 1.44, which is your epsilon, is 2.08 pounds per gallon. So this is the average volume. If you take this table, take the average, find the average of these numbers here. If you find the average of these numbers there, you will get what? You will get 2.08 ppg. Okay. Then the mass equal to 2.08. Total mass of the propant pumped is 2.08 times injected volume minus the pad volume, which is, if you calculate, you will find 72,910 pounds of propant. If you divide this by 2.2, you will get in kgs if you want to calculate in kgs. So this is in pounds. Okay. So about 30,000 kgs of propant you pumped. Okay. Yeah. So now our final aim is to find the average probed fracture width. So why are we interested in the average probed fracture width? Because the permeability of the fracture depends on the average probed fracture width. So this is the formula. So first you calculate the concentration of propant in pound per feet square of fracture. So if this is the fracture, so per foot square of this fracture, how much what is the mass of the propent you have per foot square. Okay, so in this case, total mass is what? 72,910. And then what is the area of the fracture? 2 times the fracture half length times the height of the fracture. So this formula, 1000 times 10 times 2 times 1000 times 100. So you get 0.3645 pounds per foot square of fracture. So this is the amount of propent per foot square of fracture, and you divide this by 2.2, you can get in what? Kg. Okay, so almost like what, about 15 or 16 what, about 50 grams, no, not 50 grams, about 150 grams. Okay, 150 grams of propent per foot square, something like that. Okay. So now finally you need to calculate fracture width. So width is what? Average fracture width is what? The concentration per foot square, okay, divided by 1 minus propent porosity times the propent density. Okay, so 40% porosity of the propent times 165. Where does this 0.4 and 165 come? Okay, so look at this, propent density, porosity is 0.4, so 40% porosity in the propent pack, and the density of the propent sand is 165 pounds per feet cube. So that's what we are putting there, okay, in this formula. So you get about 0.00368 foot, okay, which equates to about 0.04 inches. So this is the average width of the fracture, which is 0.04 inches. Okay, it's a bit on the lower side, but yeah, this is the calculation. So now we got the answers to all our questions. What is the fluid volume requirement? What is the propent mixing schedule? What is the propent weight requirement? And what is the probed fracture width? So using these calculations, we got all the parameters we wanted. Now please remember, this 1000 foot half fracture length is something you need to know beforehand. Okay, also the fracture height is something you need to know beforehand. And this 1000 foot fracture length depends on the area that you want to stimulate. Okay, acreage, it depends on the acreage that you have. Okay, so I hope it is clear until this part. Next, so does anyone have any question until here, or what? Does anyone have any question? Next, let us calculate the breakdown pressure. Okay, a little bit. So you know, I hope you have seen this profile before. So this is the profile. So if you start pumping fluid, so suppose you have you have made the well, you have made the perforations, and you are pumping fluid in the well bore. Okay, so the pressure will increase initially. Okay, then you will reach the leak off point, then the breakdown point, then you will reach the fracture propagation point, where you will propagate the fracture. Finally, you will get to the ISIP, which is what? Instantaneous shut-in pressure. And finally, you will get the closure pressure. Okay, so you will see all of these points. So actually, if you talk about the minimum horizontal stress estimation, then the upper limit of the minimum horizontal stress is the ISIP, and the lower limit of the minimum horizontal stress is the closure pressure. Okay, C is what? It is the breakdown pressure, point C. This means what? When you are pumping the fluid and the fracture propagates all of a sudden, then your fluid pressure will go down, right? Because the volume of the system is increasing at a rapid rate. So this is your breakdown pressure. So there is a equation that relates different rock properties to rock properties, as well as different pressures to your breakdown pressure. So P breakdown equal to 3 times the minimum horizontal stress minus the maximum horizontal stress plus T0. T0 is what? The tensile strength of the rock minus the pore pressure in the formation. Okay. So this is the P breakdown pressure. Okay. Please try to remember this. This may be good for your interviews and whatnot. Okay? Then to get the let's look at a calculation. Okay. So first you need to also get first type of for geomechanical calculations, you need to begin with what? The vertical stresses. So what is the vertical stress or the in situ stress above your head, which means what? Which is the pressure of the fluid plus the rock above a given point. Okay. So that is the density times the height divided by 144. So that this is how you calculate the overburden stress. Density is the average density of the overburden formation in pound per feet cube, and h is the depth in feet. Okay. So now you have to also calculate the two horizontal stresses, SH min and SH max. So there are different ways of calculating SH min and SH max. What you see here is this. So SH min is this formula that you have seen from before. You have already seen this formula before, okay? Except that we do not. Okay, let's take a look at that formula. So you have seen this formula. So we are just taking this much at this point. Okay, we are ignoring the tectonic stress terms. So we are only taking this much. Okay, at this point. So okay, so if you take that formula, so that gives your SH min, and plus if you add the tectonic stress, S tectonic, then you get the SH max. Okay. And obviously PP is the pore pressure, alpha is what? The Biot coefficient we discussed yesterday. Biot poroelastic coefficient. And then okay. So now let's take a look at the calculation. Okay. So in this we want to calculate the breakdown pressure. So this is the breakdown pressure calculation. So we are trying to calculate this pressure. Okay. P breakdown. So first we calculate the vertical stress or the overburden stress, SV equal to density times H divided by 144. Okay, so this is the question. A sandstone at a depth of 10,000 feet has a Poisson's ratio of 0.25 and a Biot poroelastic constant of 0.72. The average density of the overburden is 165 pounds per feet cube. The pore pressure gradient in the sandstone is 0.38 psi per foot. Assuming a tectonic stress of 2000 psi over the SH min and a tensile strength of the sandstone is 1000 psi, predict the breakdown pressure of the sandstone. So this is what we want to calculate. Okay, breakdown pressure. So you start with calculating the vertical stress, which is density times the height. Height is what? Depth, which is 10,000 divided by 144 equal to 11,500 psi. So at 10,000 foot depth, you have 11,500 psi vertical stress. Okay, that is the weight of the rock plus fluid above that point. Now calculate the minimum horizontal stress. So this is the equation. Put nu equal to 0.25, which is the Poisson's ratio, 0.25. SV, which is the vertical stress of 11,500, you put it there. Minus alpha is the Biot coefficient, which is given as 0.72. Okay, and the pore pressure is what? You are given a pore pressure gradient of 0.38 psi per foot. So if you want to calculate in psi, what will you do? You will multiply this number with the depth. So you get what? 3,800 psi. So 0.38 times 10,000, 3,800. So you put it there. So you get a SH, which is the minimum horizontal stress of 5,700 psi. Okay. Now you add 2,000 to that to calculate your SH max. You see in the previous formula, SH max equal to SH min plus S tectonic. So 5,700 plus 2,000 is 7,700. Okay. Now you are ready to calculate what? Your breakdown pressure. So P breakdown equal to 3 SH min minus SH max plus tensile strength minus pore pressure. So 3 times 5,700 minus 7,700 plus 1,000 minus 3,800. Okay, so T0 is the tensile strength of the rock, and it is given the tensile strength of the sandstone is 1,000 psi. Okay, so you put 1,000 minus the pore pressure is 3,800, which is coming from there, 3,800. So finally you calculate that the P breakdown is 6,600 psi. Okay, so that point that you see here is 6,600 psi. Now the question is, why is it important to calculate that point? Because you have a limitation on your pump power. Okay, the amount of stress that your pump can take. If your pump cannot handle this kind of stress, then you cannot use that pump. You need a more powerful pump. Okay, so that's why to understand your pump strength, you need to calculate the breakdown pressure. Okay, otherwise your rock will not break. Okay, so if the rock does not break, then your fracture will not propagate. Yes or no? So that is it. So I showed you two calculations, one for calculating the fracturing parameters, and the other one is what? Calculation of the breakdown stress. Okay, now if you have any questions, please go ahead. If not, then I have some questions. So my first question is, what are the three hydraulic fracturing propagation models? Is anybody hearing or no?
Yes, sir, we are hearing. Say.
So what are the three hydraulic fracturing propagation models? So if you talk about the simplest models, then we have this radial model. Then we have the other one is the Kristianovich Gertzma declared KGD, and then the PKN. So these are the three hydraulic fracturing models, okay? Propagation models. Which of these assumes a length of the fracture greater than the fracture height? So length much greater than height. So it is the PKN model which assumes length much greater than height. Okay. Next question is the average fracture width equal or less than the fracture width at the wellbore? What?
It's less than. Average width is
Less than, yes, correct. Yes, correct. Okay. Okay, in a fracture, in the pressure versus time graph that I just showed you, what is the highest point on the pressure versus time graph in a hydraulic fracturing? When you start pumping the fluid and you plot the pressure versus time, what is the highest point on that curve? I just showed you the calculation. So please listen again, okay? If I'm pumping the fluid and I'm recording the pressure versus time, what is the highest point on that curve?
Sure.
What?
Sure.
Yeah, breakdown pressure. Yeah, correct. Okay. What did I show? Yeah, so P breakdown is the highest point on that curve. Okay. Next question is which of these points give you a good approximation of your minimum horizontal stress?
Closure pressure.
Yeah, closure and
Instantaneous certain pressure.
yeah, exactly.
ISIP.
Exactly. So ISIP is the max estimate of your I mean ISIP is on the higher limit of your SH min, and P closure is the lower limit of your SH min. Sometimes people also go up to this point, but that is not reasonable, okay? Because at this time the pump is still running. If the pump is running, then there are other types of pressures like a near wellbore pressure, frictional pressure. So only when you shut off the pump, then you get the ISIP. So this is the time when the fracture just starts to close, okay? And this is the time P closure when the fracture has completely closed. So SH mean estimation is somewhere between that and that. Okay. Okay. Now tell me, what are the parameters that determine the fracture width? I'm not going to show you the formula. Do you remember anything? What are the different parameters that we use to calculate the fracture width? So the question is, what is the dependent variable? Yeah.
Propant concentration,
Okay.
porosity, pore pressure.
Okay. Okay, so that is the propped fracture. Okay, that is the propped fracture. So once you have pumped the propant, that is the propped fracture width. And how about unpropped fracture width? So suppose you did not pump any propant, then what parameters you need? So this thing that we calculated here, okay, this is the unpropped fracture width. This is without the propant. This is when you are pumping the pad fluid. Okay. So it depends on what? It depends on the pump rate Q. Then mu is what? Fluid viscosity. Then what? Poisson's ratio, fracture half length, shear modulus or Young's modulus, and the fracture height. Okay, so all of these things will go into calculating your unpropped fracture width. And the answer that you gave me is also correct. Okay, because I did not tell you whether I'm asking about the propped or unpropped. And so the propped fracture width is what? The propant concentration divided by porosity of the propant pack times density of the sand. Okay, so you are correct. Okay, so this is it from me. If you have any questions, please go ahead. Otherwise, we can end this lecture. Okay, so you're good.
Yes,
Oh,
sir.
so you guys are also writing the answer or what? I did not read anything. Okay, someone mentioned. Oh, Niharika was mentioning something. Okay. Okay, so this is it. Sorry, I did not read anything. I was just looking for your voice. Okay. Okay. Hello, sir.
Yes. Sir is not here actually.
Oh, okay.
Okay, sir. Then we will end the session. And thank you so much
Okay.
for your presentation, sir.
Okay. Okay. Thank you. Have a good day.
And participants, I'll request you all. We are going to end this session, and tomorrow we will have next session. It will start from 9 a.m. So thank you.
Okay. Thank you.